In the previous episodes, we developed the structural foundations: difference, refinement, closure, finite generator sectors, coherence selection. Now we stop explaining. We state the result. A stable, directed refinement system satisfying the full axiom set admits exactly one of two regimes. There is no third possibility. Either the system stabilizes into structured representation, or it collapses into instability. That is the classification theorem. Let's begin from the formal starting point. A refinement system consists of three components: a partially ordered set, a refinement relation, and a refinement operator that is continuous with respect to directed limits. Because the order is directed complete, and because refinement is continuous, the system admits a least fixed point. Closure is guaranteed, not philosophically, structurally. The stabilized sector consists of all elements unchanged under refinement. This is the closure region. From here, everything else follows. Every stabilized element admits a finite generating set, not infinite, not arbitrary, uniformly bounded. This means that local structure is finite dimensional. There is a maximum number of independent compact generators required to build any stabilized state. This bound is global. That fact alone changes everything. It means refinement does not produce unbounded combinatorial chaos. It produces constrained structure. Now consider how refinement directions act inside one of these local sectors. They act linearly. They act continuously. And crucially, at least two refinement directions are incompatible. They do not commute. That incompatibility is not decorative, it forces structure. The commutator of refinement directions closes. They form a Lie algebra. That is not imposed from physics. It is forced by refinement composition. Once you have a Lie algebra acting on a finite dimensional space, further consequences follow. Each generator sector admits a positive, definite quadratic form preserved under refinement flow. Preservation of this quadratic structure forces anti-symmetry of refinement generators relative to the inner product. In finite dimensions, anti-symmetric operators decompose into rotational blocks. Rotational blocks induce complex structure. Complex structure is not assumed. It emerges, and once complex structure is present, refinement evolution can be written in unitary form. That means refinement preserves norm. The system now carries the mathematics of unitary evolution, without ever postulating wave functions, without ever assuming Hilbert space at the start. It has emerged from structural invariance alone. Now consider invariant measures. Suppose we demand a measure that is non-negative, additive across orthogonal sectors, invariant under refinement flow, and continuous. There is only one possibility. The measure must be quadratic in the inner product. No alternative survives these constraints. The quadratic form is not chosen. It is uniquely determined. This is a structural inevitability. Now consider incompatible refinement directions again. Non-commutativity introduces dispersion. The dispersions of incompatible refinement directions are bounded from below. That bound follows directly from the geometry of inner product spaces. Minimal dispersion states arise precisely when deviation vectors align. And under canonical representation, these states assume Gaussian form. Gaussian structure is not postulated. It appears as the extremal solution to structural constraints. Now, introduce one additional condition. There exists a minimal dispersion scale, a compact width bound. No stabilized state can localize refinement direction below a fixed threshold. That threshold is structural, not inserted. Under mild analytic and symmetry assumptions, this minimal width uniquely determines how the commutator deforms at higher order. The deformation is quadratic in the incompatible direction, and its coefficient is fixed by the width bound. This is conditional deformation rigidity. The system does not freely deform. It deforms in a uniquely constrained way. Now we turn to the second regime. Assume the symmetry algebra has bounded dimension. There is a maximum number of symmetry directions available to preserve structure. Now consider what happens if interaction-induced constraint rank grows without bound. Under refinement, constraint directions accumulate, but symmetry directions remain finite. Eventually, the constraint rank exceeds symmetry support. At that point, no invariant manifold can persist. No refinement-consistent stabilization survives. Persistence collapses. This is the instability regime. We now state the classification clearly. Under the refinement axioms, exactly one of two outcomes occurs. Either the system enters the stabilized representation regime. In that regime, each local sector carries Lie algebra structure, complex structure, unitary refinement evolution, unique quadratic invariant measure, non-commutative dispersion bounds, algebraically characterized minimal states, and constrained quadratic deformation, or the system enters the instability regime, where constraint rank diverges under bounded symmetry and no invariant structure persists. There is no third option. This is not a reconstruction of quantum mechanics. It is not a speculative analogy. It is a classification result. If refinement stabilizes under bounded symmetry and finite generator width, representation theory is unavoidable. If refinement cannot stabilize under those constraints, persistence fails. Everything beyond this point is application. But the structure itself is complete. That is the theorem.